Welcome back to part 2 of section 6.4, logarithmic equations and inequalities. In part 1 you missed some pretty good fun here with question number 1, 2, 3, 4, and 5. So we'll pick up this video with question number 6. I have an equation that says solve 2 times the natural log of x equals the natural log of 4 plus the natural log of x plus 8. This question is going to test whether or not you remember the properties of logarithms we introduced in section 6.2. And I'm going to need to use 2 properties in particular. The first is the power rule, and the second is the product rule. On the left-hand side, I have 2 times the ln of x. Using the power rule, I can rewrite that as the ln of x squared. And what I should really tell you what my goal is here. My goal is to write each side of this equation as a single logarithmic expression. So it'll be the ln of something in parentheses with nothing else outside of it. So I've done that on the left-hand side by rewriting that as ln of x squared. Now on the right-hand side, I have to consolidate this to a single logarithmic expression. If you remember the product rule, we said anytime we had a sum of logarithms, that could be rewritten as a product, assuming those logarithms are of the same base, and in this case they are. So I can rewrite the ln of 4 plus the ln of x plus 8 as the ln of 4 times the quantity x plus 8. And I can expand what's inside that set of parentheses to get the ln of 4x plus 32. So now on the left and right I have an expression that's each in terms of natural logs, so I can take that expression and this expression and set them equal. That'll result in the following equation: x squared equals 4x plus 32. This is a pretty straightforward quadratic. You should know that we're going to solve for 0 on one side by getting x squared minus 4x minus 32 equals 0. And this is easily factorable into x minus 8 times the quantity x plus 4 equals 0. And if you recall the zero product property, this equation will be true when x equals 8 or x equals negative 4. So there's our final answer, and we're ready to move on to question 7. And if you were to do that, then you'd be wrong, because we have missed something very subtle but very important. What we forgot to do is go back and make sure that both of these solutions are valid in our original equation. Well, let's go back and look at our original equation. If we take a look at the two natural logs that have variable inputs, remember that the input to a logarithm has to be positive. So in this case, x plus 8 has to be greater than 0, which means x has to be greater than negative 8. Well, 8 is greater than negative 8, and negative 4 is greater than negative 8. So both those answers check out. But this is the one here that gives us a problem. ln of x has to be greater than 0. Otherwise, the ln of x will give us an error. So x equals 8 is okay, but x equals negative 4 is not. X equals negative 4 is not a solution to this equation. The only solution we have, the only one that we will report as an answer, is x equals 8. Now, if you remember what x equals negative 4 is called, what type of solution that's called, and if you're the first one in your class to tell me that, you will win a trip to the toolbox. But enough about that extra solution. Let's move on to question 7. Solve log base 3 of 2x equals log base 1/3 of 2x plus 3. Well, this is the first time we've seen anything where we have mixed bases. We have a log base 3 here, we have a log base 1/3 here, and we have a log base nothing here. Our strategy for this problem is going to be to rewrite everything in terms of a single base. And I think 3 will be the most convenient one for us to work with. So the left-hand side's already log base 3, so that's not going to change. The right-hand side is going to change quite a bit, though. So in order for me to change log base 1/3 to log base 3, I need to use the change of base formula. If you recall from our notes in section 6.2, this will be the log base 3 of 2x divided by log base 3 of 1/3. Folks, can you hear the barking? That's Mr. Vass's dogs. They are so excited because we are using properties of logarithms. I'm excited too. So excited, I need to pause the video. Okay, now that I got the dogs settled down because of how excited they were over properties of logarithms, let's go ahead and talk about this.
What you doing here, old man?
Well, Team Vass here keeps throwing interruptions at me. We have the dogs, and now we have Sam, who can't seem to let me record these high-quality videos without interruption. So hold on a second here, folks, while I take care of this distraction. All right, hopefully now we got the riffraff out of the room. The dogs are, I gave them a toy, and they're playing in the other room. Let's go ahead and see if we can finish this off. Okay, log base 3 of 1/3. Ask yourself, 3 raised to what power gives me 1/3? Clearly, that's -1. Okay, so I'm done rewriting log base 1/3 of 2x as a base 3 logarithm. Next thing I have to do is work on 3. So if I want to take 3 and rewrite it as a base 3 log, this is what my thought process has to be. 3 raised to some number, 3 raised to an exponent of 3, gives me 27. That means log base 3 of 27 is 3. Okay, so everything now is in terms of base 3. So let's go ahead and rewrite this and see what we've got. We have the log base 3 of 2x equals log base 3 of 2x divided by -1, which is negative log base 3 of 2x plus log base 3 of 27. Okay, the left-hand side, we're good. We've got the log base 3 of 2x. There's nothing else we need to do here. But we can still consolidate our right-hand side, and I'm going to start by rewriting this as the log base 3 of 27 minus the log base 3 of 2x. The reason why I rewrote it this way is that hopefully you're able to see the quotient rule built into this problem. Anytime I have a difference of two logs, they can be rewritten as a quotient. Left-hand side is still log base 3 of 2x, but my right-hand side is log base 3 of 27 divided by 2x. We're getting really close, folks. We now have two base 3 logarithms, one on the left, one on the right. So we can set the two arguments equal. We can write a new equation that says 2x equals 27 over 2x. And then we'll be able to solve that. Okay, let's take a look here at problem number 8. This one is really tricky, folks. We have the natural log of the natural log of 2x equals 16. So we haven't seen one like this before where we have a logarithm buried inside of another logarithm. So what I'd like to do is see if maybe I can simplify this problem. I'm going to go ahead and say, let's let this thing right here equal u. So I'm just going to kind of introduce another variable to this problem. And now I can rewrite this as the natural log of u equals 16. Well, I can rewrite this as an exponential. E to the 16th power equals u. So what I have now are two different things that actually equal u. I have this right here, the ln of 2x equals u, and e to the 16th equals u. So let's go ahead and take these two ideas and combine them here into a new equation that looks like this. The ln of 2x equals e to the 16th. I can rewrite this as a or as an exponential equation by saying e raised to the e to the 16th equals 2x. Folks, I think we're almost home. Now to get x all by itself, all I have to do is divide both sides by 2, and that gives me x equals 1/2 times e raised to the e to the 16th power. And I know, folks, that looks like an absolutely crazy answer, but it is 100% correct. The last thing we have to do on this one is just make sure that our solution doesn't violate any domain restrictions for logarithmic functions. So we have the ln of 2x, our input is x, and if we recall, the input to any logarithmic function has to be positive. So the ln of 2x, that means 2x has to be positive, and e is a positive number. When I raise that to the 16th power, it's still positive. If I use that as an exponent on e, still positive. If I cut that number in half, it's still positive. So this solution right here works. The only other possible domain restriction I have here would be if this variable we introduced, if u was not greater than 0. Well, u is e to the 16th power, and that's positive. So again, I just wanted to make sure we look back at all the different parts of this solution and make sure we didn't introduce any extraneous solutions. Let's go ahead and look at problem number 9. Question number 9 introduces something new to us in this lesson, and that's the introduction of an inequality. So we need to take a look at this problem a little differently than we have the previous ones. Let's first talk about domain restrictions. I know in the past couple of problems we've talked about that at the end, but I want to talk about it at the beginning for this one. My denominator here is x squared, so that means x cannot equal 0. I have a natural log function here. The input to that is just x, so x has to be greater than 0. If you take a look at those two restrictions, x greater than 0 is more restrictive, so that's going to be our basically the domain restriction for this problem. Now let's take a look at the numerator. So we have this numerator here that is 7 minus the natural log of x. And anytime we've done these inequality problems, we try to find out the 0 of our numerator. So let's do that now. 7 minus ln of x equals 0. Let's go ahead and rewrite this as 7 equals the natural log of x. At this point, I would rewrite this logarithm as an exponential. E to the 7th equals x. Okay, so this is the value that makes our numerator equal to 0. I think it's time that we look at a sign chart. On our sign chart, we're going to put a couple different values. We're going to put 0. Because 0 is restricted from our domain. To the left of 0, we don't have anything because we said that x has to be greater than 0. But to the right of the 0, we have this e to the 7th power. E to the 7th will make, if x equals e to the 7th, our numerator will equal 0 and the whole expression will equal 0. So now we have to look at the behavior of 7 minus ln of x. Well, if x is greater than e to the 7th, we'll be doing 7 minus something bigger than 7. So our sign chart is going to be negative out here based on the sign of the numerator. The denominator is always positive because any real number squared is positive. So out here, 7 minus any number bigger than e to the 7th will give us a negative value. And you should test that on your calculator right now. Do 7 minus e to the 8, or 7 minus the natural log of e to the 8th, and verify that for yourself that it's negative. To the left of e to the 7th, we'll have a positive output. So the solution to this inequality is going to be any time we're negative. So x is the values from e to the 7th to infinity. And that's our solution. Number 10 is the last problem we're going to look at for this section, and it is another inequality involving logarithms. The way I'm going to start this one is I'm going to rewrite everything as an exponential. So the log base 10 of 2x means that 10 raised to some exponent has to be 2x. So on the left-hand side of this inequality, it's going to look like this. 10 raised to the 1.5 power is less than or equal to 2x, which is less than or equal to 10 raised to the 2.1 power. I'm going to let you take a look at that for a second and make sure you believe that based on how I've written it. So understanding how to rewrite a logarithm as an exponential produces the following inequality. Now to finish this one off, to have the interval the interval values of x that make this equation true, I'm going to divide everything by 2. So that'll give me 10 raised to the 1.5 power divided by 2 is less than or equal to x, which is less than or equal to 10 raised to the 2.1 power, all divided by 2. So I would encourage you to pick some test values to check this one out. Just make sure you believe the solution. But remember, the input to the logarithmic function has to be positive. Both the left-hand side and the right-hand side of this interval will be positive because 10 is a positive number raised to an exponent, and then divided by 2 will still give us a positive output. Folks, that's it for section 6.4, logarithmic equations and inequalities. Good luck to you in WebAssign for this section.